investigating robustness of multi-robot trajectory planners to communication dropouts. The motivation. The generation of efficiency trajectories for swarm robots is important for different applications such as performance and search and rescue. However, in real life, there is not such thing as perfect communication. We have many issues, for example, latency, dropped packets, limited range and bandwidth communication, and the robot itself can fail. Our goal is to design a multi-agent trajectory generation algorithm that can handle communication failure, and we will be focusing more in the system-wide communication failure.
We'll briefly cover the literature. So when making decisions with teams, we can make decisions in a centralized manner, where one agent makes decisions for all of the other agents, or we can make decisions in a decentralized manner, where each agent makes decisions for itself. Centralized is more optimal, but decentralized is far more robust to issues such as communication failure. And of course, there are hybrid approaches between these two. In decentralized approaches, we also need to coordinate between the agents. And this coordination can be explicit, where the agents explicitly say, one agent is going to do this task, one agent is going to do another task, or implicit. And implicit is far less computationally expensive and better when communication is weak, because each agent is approximating the behavior of the agents around it to attempt to figure out what they're going to do and the best thing that each agent can do for itself.
Right, so I'm going to be talking about the chosen algorithm and essentially the goal of this project, which was to take an algorithm that didn't really consider what happens when communication does drop out and to try and modify it so that it does become robust. So the algorithm that we chose is online trajectory generation with distributed model predictive control for multi-robot motion planning. And we chose this algorithm because A, it's state-of-the-art, and B, it does handle real-world situations. All right, so the NPC structure is to minimize these quadratic costs subject to linear constraints. So the costs we're minimizing is an error cost, which penalizes distance to the goal, an energy cost, which penalizes derivatives, and a violation that makes sure that the agents are sufficient distance away. And this is such that trajectory is feasible, state constraints are satisfied, and collisions are obviously avoided. All right, so here we have two agents and they're about to collide. And we know they're about to collide because we have some scaling of the distance between them being greater than some minimum threshold amount. So how do we actually account for this? Well, there's two approaches. One, we can use a buffered Voronoi cell approach, which is at every time step, the agents share their current position. And essentially at every time step, they're just forced to stay in their own buffered Voronoi cell. The other approach is an on-demand collision avoidance approach. So here, instead of just sharing positions, they also share future trajectories. And given that they have each other's future trajectory, the agents are forced to stay in their separating hyperplane. And when they produce a new trajectory, that trajectory should also be in that hyperplane. All right. Implementation.
We will be working with 15 drones. The workspace will be smaller than the one discussed in the paper, and we will be using a random initial states and goal states. The goal is to find a safe and feasible trajectory from the initial to the goal states, updating online communication for robustness. The measurements that we will have are the transition time and the number of collisions. The transition time being the number of NPC interaction that it takes to complete the whole task, and the number of collisions is the number of times that two drones are closer than 30 centimeters. The communication can fail in different ways, but we will focus more in these two, the stochastic and the periodic. The stochastic is in which we have C as a probability of no communication in the beginning of every time step, and the periodic is the periodic of failure that can happen from half of the horizon to the 1.5 the horizon, and we measure the proportion of no communication with C. The values that we use it for C are the following.
All right, so to compare our on-demand approach to some benchmarks, we needed to have two benchmarks. So first we had a performance benchmark, and this is essentially a benchmark that in the event of communication dropout, the agents just assume that the other ones don't exist and go about their trajectory. The second benchmark we had was a safety benchmark. So in the event of communication dropouts, the agents actually just stop. So the problem with the safety benchmark is that A, it's conservative, and B, it might actually be infeasible. So next slide, please. So we had another approach, which is to use a static buffered Voronoi cell approach. So in this approach, instead of just stopping, well, we have the buffered Voronoi cells, or rather we can calculate them from the last time step. And so when communication drops out, the agents can just stay in their own BVC, and this can, allow them to slowly go to a halt instead of just immediately stop. Our on-demand implementation was to use the last known trajectories of the drone at the last time step, and instead of minimizing an error to the goal, we're going to penalize distances from the drone's last trajectory so that they can stay within the trajectory and hopefully not crash into each other.
Going on to the results, we tested every single approach with every communication level and communication failure type 25 times. And the results for mission time are here. We see that the performance is as expected. It actually improves as the communication deteriorates. However, the safety benchmark actually deteriorates very rapidly, especially in the stochastic case. The other two approaches, BVC and on-demand, perform relatively similarly to each other. In terms of number of collisions, we see that the performance benchmark performs terribly, colliding quite significantly, and the on-demand doesn't perform that much better. On the other hand, the safety and BVC approaches both reduce the number of collisions quite significantly. In terms of computational cost, in general, we simply note that all of the approaches have roughly the same computational cost. Overall, the benchmarks performed as intended, and the approaches are surprisingly somewhat similar between the stochastic and the periodic case, except for the safety benchmark, which is significantly worse in the stochastic case. Overall, our recommendation is the BVC approach because it seems to have comparable safety to the safety benchmark and comparable performance to the other three approaches.
For the conclusion, we consider that there are future jobs that can be tested in the project with different communication failures, such as communication delays and individual drone failures, rather than the wide system-wide communication that we discussed. There are different testing in different approaches. For example, the various functions and other state-of-the-art approaches. And the problem itself is that in real life, communication is unreliable. And we saw that this problem is not addressed in many of the multi-agent coordination papers that we discussed. We tried to test in our experiments different types of communication failures and correcting a naive algorithms with various approaches. And we conclude that there is a trade-off between the performance and safety. And the approach that we consider is the best is the BVC that handles pretty well this trade-off. And it is a simple addition to most of the algorithms that allows for safety.
Thank you very much.